statistics, the AND rule, and tree diagrams. Now let's have a look at the product rule. First, we need to introduce the idea of independent events. Two or more events are independent if the outcome of one in no way affects the outcome of the other. Let's look at an example. If two dice are thrown together, then the score on one will not affect how the other lands or its score. These are independent events. Let's look at another example. If two events are, it is raining and John takes an umbrella to school, then whether it rains or not will affect John's decision to take an umbrella with him. These events are not independent. Now, this is important for the product rule. If two events are independent, then the probability of them both being successful is the product of their individual probabilities. Now, this can be extended to more than two events. So, what we have is if A and B are independent events, then the probability of A and B both happening is equal to the probability of A times the probability of B. So, for example, if a coin and a dice are thrown together, what's the probability of getting a heads and a score of at least 5? Now, to solve this, on the coin, the probability of getting a head is a half, and on the dice, the probability of getting a score greater than or equal to 5 is 2 out of 6. There are two possible outcomes, greater or equal to 5, that's 5 or 6, out of a total of 6 outcomes. These events are independent. However the coin lands will not affect how the dice lands. So, the probability of getting a head and a score of greater or equal to 5 is equal to a half times 2/6. Well, that cancels down to 1/6. Now we can see this result by other methods. We can represent this on a table or probability space. To the left of the table we've got the coin, and that has two possible outcomes, heads or tails. At the bottom of the table we've got the dice, and that has 6 possible outcomes, 1, 2, 3, 4, 5 and 6. Now that means the top left-hand corner represents heads and a 1. The next one along is heads and a 2, heads and a 3 and so on, and the bottom row is tails and a 1, tails and a 2, tails and a 3 and so on. Now all outcomes are represented in the table and they're all equally likely. There are 2 out of the 12 successful outcomes. That's heads 5 and heads 6. So the probability of getting a score of heads and a score greater or equal to 5 is 2 out of 12, which is 1/6. We can also solve this on a tree diagram. When we throw the coin, there are 2 branches, heads or tails, and each of these has a probability of a half. Now for each coin branch, there are 2 dice branches, greater or equal to 5 or less than 5, and these have probabilities 2/6 and 4/6. Now we want heads and then greater or equal to 5, so we follow that along the branches, and that gives us the probability of a head and then a score of greater or equal to 5 is a half times 2/6, which is 2/12 or 1/6. Let's have a look at an example of a tree diagram. A driver passes 2 sets of traffic lights on his way home from work. If the lights are green, he goes straight through, otherwise he comes to a stop. He notices at the first lights the probability of green is a half, and at the second set of lights he notices the probability of a green is a third. To begin with, draw a tree diagram of the situation. Well, to do this, let's look at the first set of lights. There are 2 options. Either he goes or he stops, and each of those has a probability of a half. Now, if he goes, there are again 2 options. Either he goes or he stops, but this time the probabilities are 1/3 and 2/3. If he stops, we get the same situation. He can go or stop with probabilities 1/3 or 2/3. Now, to get the final probabilities, we multiply along the arms. So, if the lights are go and then go, that's 1/2 times 1/3, which equals 1/6. If the lights are go and then stop, the probability is 1/2 times 2/3, which is 2/6. If the lights are stop and then go, the probability is 1/2 times 1/3, which is 1/6. And if the results are stop and then stop, the probability is 1/2 times 2/3, which is 2/6. Now in part 1, we're asked to find the probability that he stops at both lights. Well, if he's going to stop at both lights, that's got to be a stop and then a stop, which gives a probability of 2/6, or 1/3. In part 2, he stops at just one light. Now to stop at one light, he can go and then stop, or stop and then go. So that's 2/6 plus 1/6, which is 3/6, which cancels down to 1/2. And in part 3, we're asked, what is the probability that he does not stop? Well, if he doesn't stop, then he goes and goes again, and that has a probability of 1/6. Now, in part 4, we're asked, during 90 working days, estimate how many times he would get home without stopping at the lights. Well, the expectation is the probability times the number of journeys, which is 1/6 times 90, which is 15. So he would expect to get home without stopping 15 times. That means he would get home without stopping approximately 15 times. Let's have a look at another example of a tree diagram. A bag contains 4 red, 5 green and 3 blue marbles. 2 marbles are taken at random without replacement. In the first part, we're asked to represent this on a tree diagram. So, let's draw the tree diagram. Now on the first pick, there are 3 options: a red, a green or a blue marble. Altogether, there are 12 marbles. Now there are 4 red marbles, so the probability of picking a red marble is 4 out of 12. The probability of picking a green marble is 5 out of 12, and the probability of picking a blue is 3 out of 12. Now, for the second pick, if we've already chosen a red, there are 3 options: red, green or blue. There are only 3 reds left and 11 marbles in the bag, so the probability of picking a second red is 3 over 11. There are 5 green marbles left out of 11, so the probability of picking a green is 5 out of 11, and the probability of picking a blue is 3 out of 11. For the second pick, there are again 3 options: red, green or blue. If we've already picked a green, there are 4 red marbles left out of 11, so the probability of getting a red is 4 out of 11. There are now only 4 greens left, so the probability of picking a green is 4 out of 11, and the probability of picking a blue is still 3 out of 11. If we have chosen a blue, there are still 3 options for the second pick. That's red, green or blue. There are 4 reds left, so the probability is 4 over 11. There are 5 greens left, so that's 5 over 11. But for the blues, there are only 2 of them left, so the probability of picking a blue is only 2 out of 11. Now to work out the final probabilities, we multiply along the arms. Now that gives us a red and a red is 4 over 12 times 3 over 11, which is 12 over 132. For a red and a green, we have 4 over 12 times 5 over 11, which is 20 over 132. And for a red and then a blue, we've got 4 over 12 times 3 over 11, or 12 over 132. Now, if on the first pick we've got a green, then a green and a red is 5 over 12 times 4 over 11, which is 20 over 132. A green and a green is 5 over 12 times 4 over 11, which is 20 over 132. And a green and a blue is 5 over 12 times 3 over 11, which is 15 over 132. Now, if we have a blue and then a red, that's 3 over 12 times 4 over 11, or 12 over 132. If we have a blue and a green, that's 3 over 12 times 5 over 11, which is 15 over 132. And if we have a blue and a blue, that's 3 over 12 times 2 over 11, which is 6 over 132. Now for part 2, we're asked to find the probability of getting 2 red marbles. Well, the probability of getting a red and then a red we can see is 12 over 132, which cancels down to 1 over 11. In part 3, we're asked, find the probability of getting a red and a green marble. Well, to get a red and a green marble, we can get a red and then a green, or we can get a green and then a red. Now that gives us 20 over 132 plus 20 over 132, which is 40 over 132, which cancels down to 10 over 33. And in part 4, we're asked to find the probability of getting at least 1 blue marble. Well, to get 1 blue marble, we could get a red and a blue. We could get a green and a blue. We could get a blue and a red. We could get a blue and a green. And we could get a blue and a blue. Now that's 12 over 132 plus 15 over 132 plus 12 over 132 plus 15 over 132 plus 6 over 132, which works out to be 60 over 132, or 5 over 11. And in part 5, we're asked to find the probability that 2 marbles have the same colour. Well, to get 2 marbles the same colour, we could have a red and a red, or a green and a green, or a blue and a blue. So, a red and a red is 12 over 132, or means add. A green and a green is 20 over 132, or we could get a blue and a blue, so that's add 6 over 132. Now altogether that gives 38 over 132, or we can cancel that to 19 over 66.